So I'll be recording this class. First of all, going into this chapter of organic chemistry, let's first know some definitions, okay? Such as what is a normal salt, okay? So when salts, okay, have only one type of cation and one type of anion, they are called, okay, normal salt. Now, when we are talking about this, let's take some examples from a very basic. Uh, we will say NaCl, आपका टेबल सॉल्ट जो है, ठीक है, खाने में आप जो यूज करते हैं, या फिर KCl, ठीक है ना, KNO3, एक ही कैटायन एक ही एनायन है, या तो फिर Na2SO4, इसमें सोडियम है और साथ में आपका क्या है, सल्फेट आयन है, या फिर NH4 प्लस Cl माइनस, ऐसे टाइप ऑफ सॉल्ट्स को हम लोग नॉर्मल सॉल्ट्स कहेंगे, राइट? तो ETC। मिक्स सॉल्ट्स क्या होगा? मिक्स्ड सॉल्ट्स क्या होते हैं, राइट? Say suppose when only one type of cation okay is present, but more than one type of anion is there, ठीक है ना? तो इसको हम लोग मिक्स सॉल्ट्स कहेंगे। जैसे देख लो एग्जाम्पल पे हम लोग क्या बोल सकते हैं कि CaOCl, ठीक है, इसको हम लोग क्या बोलते हैं, ब्लीचिंग पाउडर, ऑलराइट, और यू कैन से MgOHCl, or we can say FeOH whole twice Cl. So similarly, one can say that when more than one type of cation is present, but only one anion is there. पहले में क्या था? In the before case we had one type of cation and two types of anion, right? But here in this case we are having more than one type of cation but only one type of anion. So these can also be called as mixed salts. Example, let's say Na plus NH4 plus HPO4. We are having sodium and ammonium, and then we are having this biphosphate ion, or we can have K plus Na plus C2O4. This can also be there. Okay, we can also have the sodium, potassium tartarate. Okay, this is also a mixed salt. All right, or we can also have, say, Na. Okay, let's finish it there. Okay, the sodium potassium tartrate is also called Rochelle salt. Okay, we will come across this salt when we do the test for aldehydes in organic chemistry. Okay, so this also is a mixed salt. Now, can there be another type of salt? There is another type of salt which is known as a double salt. Okay, so what is a double salt? First of all, these salts, okay, appear to form an aggregate. Okay, just aggregate of two simpler salts. Okay, each capable of independent existence. They are stable only in solid state. They are stable only in solid state. तो दो इंडिविजुअल सॉल्ट्स है, मान लो वो अग्रीगेट करेंगे, क्रिस्टलाइज करेंगे और सॉलिड में ही स्टेबल है, सोल्यूशन में स्टेबल नहीं है, राइट? जैसे कि मान के चलो KCl के साथ अगर MgCl2 एक इंडिविजुअल सॉल्ट है, KCl भी एक इंडिविजुअल सॉल्ट है, मतलब एक नॉर्मल सॉल्ट है या सिंपल सॉल्ट है। अब ये दोनों अगर छोड़ दे हम सोल्यूशन में और उनको क्रिस्टलाइज करने दे तो ऐसे ही एग्रीगेट बन जाएंगे, और इसको हम लोग क्या कहते हैं? इसका नाम क्या है? कार्नेलाइट। तो आपको सवाल पूछा जाएगा कैसे? आपको नेम दिया जाएगा और पूछा जाएगा कि is this a double salt? Okay, sometimes like that they will give you, or say they are giving you K2SO4 Al2SO4 whole thrice dot 20H420. This is known as potash alum. Okay, cellular ফিটকিরি use করা হয়, that is this compound. Okay, or any type of alum. Okay, so any type of alum will be having a general formula. What is the general formula? M should be +2 oxidation state. The other metal ion should be in +3 oxidation state. Okay, so MSO4 M2SO4 whole thrice dot 24H2O. Okay, so this is the general formula for alum and all alums are basically your double salts. Okay. Similarly, you can also have chrome alums. Okay, something like FeSO4. In place of aluminium, you're going to have chromium over here. So chromium is in +3 oxidation state. SO4 whole thrice dot 24H2O. Okay, this is called a chrome alum. When we will call this a chrome alum? Whenever we are having, in place of aluminium, a chromium out there, and if you check, aluminium is also +3 oxidation state, whereas chromium is also in +3 oxidation state. Another salt, we are using this salt in the redox titration reactions known as Mohr salt. This is basically what? FeSO4 NH4 whole twice SO4 dot 6H2O. So for your exam purpose, they will either give you the formula of the salt or they will give you the name of the salt and they will ask you whether this is a double salt or not. Please tell. Okay. Understood? Now, next one is called a two-tone salt. What is the two-tone salt? It is basically M2SO4. So this M can be Na or potassium. CuSO4. Okay. Dot 6H2O. So what you are seeing that all these double salts are having some water of crystallization along with them. Okay. Strictly speaking, they are only stable in the solid state. But if you let these salts in solution, the salt will dissociate completely into these individual ions. So one property that is common among the normal salt, the mixed salt and the double salt is that if you dissolve these salts, okay, in the aqueous solution, then the individual ions will be formed and you will get the chemical test for each of these ions inside the solution. Okay. Now, having said this, let's take an example. Okay. So, what is that? Suppose I have dissolved NaCl in water. All right. So that would mean that Na will go inside water and will be surrounded by the water molecules. Okay. That means it will be hydrated. All right. Similarly, so if you're doing a test for sodium or a chlorine, then you will get the chemical test for both. Suppose similarly, if you have K plus Na plus C2O4, that is one mixed salt inside water, then you will get the test for K plus, also the test for the Na plus, also you will get the test for oxalate ion. Okay, so I might ask you how many ions will be formed when you dissolve these salts inside the water. Okay. Similarly, if I give you KCl, that is carnallite MgCl2 dot 2H2O, which has been dissolved in water, and if I ask you if you do what are the ions that will be formed, so you will see, sir, one potassium ion will be formed. Along with that, we will have a magnesium ion will be formed. 3 moles of chlorine ion will be formed, and that is what I will get. All right. So in total, how many ions are formed when carnallite dissolves? You will say, so 2 and 3, so that is 5 ions in total. Okay. Similarly for the K plus NaC2O4, you will say, sir, there are 3 ions that will be formed inside solution. Alright. Now, there are certain salts which are known as complex salts. Okay. Which, if you dissolve in water, so suppose if I dissolve K4 FeCN6 inside water, then out here you're seeing something new. I have used a third bracket over here. There is a first bracket. Okay. So what is the meaning of this? So what you will find that there are only 4 K plus ions are formed inside the solution, and along with that, the cyanide ions are now not being released. Neither is the iron released inside the solution. But this unit that is within the third bracket, that is being released. थर्ड ब्रैकेट के अंदर जो यूनिट है वो रिलीज हो रहा है अलग से, और उसके साथ आपका 4 पोटेशियम आयंस रिलीज हो रहे हैं. तो ऐसा जो थर्ड ब्रैकेट के अंदर मैंने ये यूनिट को लिखा है, इसी को हम लोग कॉम्प्लेक्स आयन कहते हैं. ये पहली बात है. नाउ इफ यू ट्राई से कंपेयर some KCN, okay, or some FeCl3, and you have dissolved this in water, then what you will find that there are potassium ions, along with that the Cn ions will be released in the solution, and if you do the test for both, you will get the test, that is for a potassium or for the Cn ion. But when you are dissolving this potassium, that is K4FeCN6, and if you try to do the test for this Cn ion, there is no test. So it is hidden, as if that it is not there. So this type of behavior is complex to us. This type of behavior is complex to us, that is why it is called complex ion. Okay, similarly, if you dissolve FeCl3 or say FeCl2, then it is forming Fe2 plus aqueous. Along with that, 2 Cl minus ions will be released. Okay. Now, if you try to do a test or chemical test for this Fe2 ion, you will get the test for the Fe2 ion. Also the test for the chloride ion. But when you are dissolving the K4 FeCN6, and if you try to do the test for the Fe2 ion over here, we will learn how to find out the oxidation states of these particular ions. Okay, in this complex ions, okay, later on. So if you try to do a chemical test for this Fe2 over here, then you will see that there is no chemical test of Fe2 is given by this salt. So when K4FeCl6 is dissolved in water and you are trying to do a test for iron, you will not get any test for iron. But if you are dissolving FeCl2 inside water and if you do a test for iron 2, you will get a test for iron 2. So this type of complexity, that a salt you are dissolving, it is containing iron, but it is some is giving the test and some is not giving the test. So when it is not giving the test, this behavior is complex. Similarly, if you are dissolving KCN and then you try to do the test for Cn, you are getting the test for the Cn, but when you are dissolving K4FeCN6, which is also containing Cn, but if you do the test for the Cn, you are not getting any test. So this behavior is again complex behavior. So whenever we see such complex behavior where ions are present, whether it can be positive or negative, but the tests are not given by that particular ion on dissolution in water, this type of behavior is complex. So there must be some complex ion inside the solution. Okay. The idea of representing complex ion like this was given by Alfred Werner. All right. So we will be giving you this historical uh, event that took place, and it started with a scientist, okay, because he made some observations. His name is Tassert. So Tassert. So Tassert made an observation, isolated basically, we will say, a an orange colored compound, that is COCl3 dot 6NH3. That is how it was initially represented. और उसको कैसे मिला ये? Obtained on standing. Standing माने you mix certain things and you leave it under air, okay? On standing an ammonical solution means a solution that is containing ammonia, okay? Aqueous ammonia of cobalt, okay? Cobalt 2 chloride, okay? That means the oxidation state of cobalt is +2 over here. Now, this thing was obtained around, say, 1798. He had made this observation, okay? People were interested with this compound, and this same compound, please understand, so it was first of all made, the observation was made in 1798, around that time, okay? The same compound, okay, can now be easily prepared. How are you going to prepare it? In high yield. High yield means, say, before it was prepared only 20%, okay? Now it can be prepared at around 70-80%. So that is how, what we mean by saying high yield. By air oxidation, okay, of ammoniacal solution of cobalt 2 chloride in presence of active charcoal, okay, as catalyst. So if you want to oxidize the cobalt 2 chloride which is present in ammoniacal solution, then one can use the active charcoal catalyst, and this thing can be achieved, okay. So Tassert had made these observations, in which what he saw, that when cobalt 2 aqueous ammonia solution uh, was kept, it turned brown, and when exposed to air, the color changed to wine red on boiling, okay. That is what his observation was. And later on, Fermi showed that the cobalt 2 solution of ammonia was basically oxidized to cobalt 3. So keeping it in air, cobalt 2 goes to cobalt 3. That is the chemistry behind it. And at least 6 ammonia molecules were associated with it. That means there are 6 ammonia molecules in this compound. But how these 6 ammonia molecules were arranged, okay, or linked, nobody understood at that time. That is what the historical account of this is. All right. Beside this, okay, yeah. Beside this, another observation was made. Okay, and this observation is what in around say 1827. All right, a scientist called Gies isolated a compound. I'm just giving you the historical account. All right, he had isolated the compound, which is basically PtCl2. That is how it was written before. Okay, C2H4. So this is how it was written before. Later on, when Werner's theory was given and people understood how these things are arranged, okay, so later on it has been found to be, how is it written? KPtCl3 C2H4. So initially it was written like almost like we have been writing the double salts, but later on you can see that it has been written with a third bracket. Inside that we have one unit and then we have an ion to balance the charge of this unit that is inside the third bracket. Okay, कहने का मतलब ये है पहले पहले तो ये लोग क्या लिखे थे ऐसे PtCl2.KCl.CH4 देखने में कैसे लग रहा है कि जैसे हम लोग पहले डबल सॉल्ट्स को लिखे थे वैसे है, लेकिन बाद में जब वर्नर ने थ्योरी दिया लोगों को समझ में आया इनको कैसे लिखना है, तो लेटर ऑन हम लोगों ने इसको ऐसे लिखा है. ठीक है, तो ऐसा नहीं है कि वार्नर ने पहले से ही सब कुछ दिया, लोगों ने पहले कुछ ऑब्जर्वेशंस किए थे. ठीक है, उसके बाद वार्नर ने अपना थ्योरी दिया कि इनको कैसे हम समझ सकते हैं. ठीक है, ये भी जान लीजिए कि दिस इज द फर्स्ट organometallic compound isolated. ऑर्गेनोमेटेलिक का मतलब क्या है? मेटल और कार्बन का जब बॉन्ड हो जाए किसी कंपाउंड में तो उसको हम लोग ऑर्गेनोमेटेलिक कंपाउंड कहेंगे. डेफिनेशन क्या है ऑर्गेनोमेटेलिक कंपाउंड के? डायरेक्ट कार्बन और मेटल का जब कोई भी बॉन्ड हो, सिग्मा बॉन्ड हो, उसको हम लोग ऑर्गेनोमेटेलिक कंपाउंड कहेंगे. एंड फ्यू मोर सॉल्ट्स that were isolated. This is called Magnus green salt. Again isolated at around 1828. It was initially again written like P2Cl2 2NH3, but later on it was formulated as, so that is after Werner gave its theory, PtNH3 whole 4 PtCl4. So we'll be discussing this all in details, okay, later on. Another one was this salt. Again it is written something like CrSCN whole thrice, okay, NH4 SCN dot 2NH3, and now it is written as, now it is formulated as what? NH4 Cr NH3 whole twice NCS whole 4. So you can see that there is a change in the trend. How is the change in the trend? Initially these were written like that, And after Warner gave its theory, the same salts were given a new type of formulation in which we have a inclusion of the concept of keeping something inside a third bracket, all right, and the rest is outside the third bracket. Okay, so what is this new idea that Warner gave? Now that we will be discussing in detail. Okay, all right. So what is that thing? Let's understand. So these were the Warner's idea. Okay, so we will be now basically discussing Warner's theory. So he gave two fundamental ideas. Okay, what is that idea? In a coordination complex, that means the complexes that we have written over here, like this one, okay, or say here this one, or say here this one, okay. A metal ion is engaged, that means linked, in strong binding with certain number of neutral, okay, and or anionic groups in the first sphere of attraction. और इसको हम लोग क्या कहेंगे? इसको हम लोग कहेंगे क्या? Called the coordination sphere. That means if you have a metal ion like this, suppose, then it is joined or engaged to neutral or anionic groups. Let's call these groups as L. Okay, so this is how it is surrounded, and this number of groups surrounding this metal ion will be called as the coordination number. Okay, or the surrounding environment that it has created, this is called the coordination zone or coordination sphere. दूसरा बात क्या बोला उसने? What is the second thing that he said? The metal ion is surrounded by the neutral, sorry, and or anionic groups in the coordination zone in a definite geometrical arrangement. इसका मतलब क्या है? ये जो लाइगेंड्स हैं यहाँ पे, जिनको हम बाद में बोलेंगे लाइगेंड्स, और एटम्स और ग्रुप्स को हम लोग लाइगेंड्स बोलेंगे, ये जो एटम और ग्रुप्स यहाँ पे हैं, जो ये सराउंडिंग कर रहे हैं इस मेटल आयन को, इनका एक स्पेसिफिक ज्योमेट्री होगा, ठीक है ना। इनका क्या होगा, एक स्पेसिफिक ज्योमेट्री होगा। और फिर बाद में हम लोग जानेंगे कि ये जो दो टाइप ऑफ थ्योरी इन्होंने यहाँ पे दिया है, फिर बाद में वार्नर ने फिर इसको फर्दर डेवलप करके कहा कि वार्नर proposed that metals have two types of ठीक है वैलेंसी। वो वैलेंसी क्या है, वो वैलेंसी क्या है? एक उसने कहा प्राइमरी वैलेंसी और दूसरा उसने कहा बी सेकेंडरी वैलेंसी। हम लोग बाद में जानेंगे कि प्राइमरी वैलेंसी is basically now called oxidation number of metal, as simple as that. That is what we will come to know. And secondary valency, okay, is called the coordination number. That is the number of atoms or groups surrounding the metal ion. Okay, surrounding the metal ion. Now, these are the definitions that we have come to know. Okay, right? These are the definitions that we have come to know as said by these people. Now, this primary valency or this oxidation state, how it can be satisfied? The primary valency which is the basically oxidation state, okay, can be satisfied by requisite number of anions or negative groups can be inside the coordination sphere or outside. Now let me give you some examples, otherwise it will be difficult for you to further understand what I'm exactly saying over here. Okay. So Warner has given us two concepts, that what is it? Primary valency and secondary valency. Okay. And he is saying further that primary valency is nothing but your oxidation number and secondary valency is basically your coordination number. So what is this basically? Let us take one example. Okay. So if I say M is the metal, L is the group or the atom, where I am giving this as N. N indicates in the subscript the number of ligands or atoms or groups surrounding this metal surrounding this metal in the coordination sphere, or we can say this to be inside the secondary valency. Okay, so M is the metal, L is what, the ligand, which can be a group or an atom, N is the number of ligands or group or atom. Okay, so we will say this is the metal. First of all, this is the ligand, which can be a group or it can be some atom, ion, isn't it? N is the number of such ligands. All right. Say this is X. This X is nothing but, we will say, the oxidation state. All right. Or which is called as to be the primary valency. Okay. This number of ligand is basically your secondary valency. It is also called the coordination number. All right. And outside here, let's say this is M. This M can be either neutral, it can be negative. Okay. It can be negative or it can also be positive. This charge. Okay. Say this charge. That is the charge outside the complex. All right. So whatever you have studied in the lecture so far, I have summarized the whole thing in this one little space over here. This is exactly what Werner said. That we have a metal ion. This is the metal ion, which can be surrounded by atoms or groups which are called as ligands, where N is the number of such metal ions, number of such ligands. Okay. X, if this is the charge or oxidation state of the metal ion. Okay, this is also called the primary valency. This N is called what? Secondary valency, or it can also be called as the coordination number. That is the number of ligands that are surrounding the complex ion. And this total unit over here, this is your complex ion. I hope things are clear so far. Bolo yes or no?
Yes, sir.
Okay. So this is what it is. All right. Now, in the next section, we will see how complexes can be anionic, cationic, or neutral. Okay. So let's consider complexes. Okay. And they can be cationic complexes, anionic complexes, and even neutral complexes. Okay. So let's do the cationic complexes first. Let's say I have given you FeH2O whole 6 and outside it is plus 3. Okay. Just follow what I am doing over here. Now, if somebody is asking me what is the charge outside this complex, you will say positive, so it is obviously going to be a cationic complex. There is no doubt about it. This water, as you can see over here, there are 6 such water molecules. So if somebody says coordination number, then what should be my answer? 6. Okay. If somebody says what is the ligand, then we will say it is H2O. What is the central metal? Iron. We will say it is Fe3 plus. Why Fe3 plus? Because this particular ligand is having charge 0. If I consider this to be as X, then I will say X0 equal to plus 3. Therefore, the value of X will be plus 3. And that is how I found out the oxidation state of the central metal ion, or I should say the primary valency of the central metal ion. Okay, let's consider this one now. I have given you over here NiH2O whole 6 2 plus. So what is the coordination number out here? Give it a try. What is the coordination number? Bolo.
So 6, sir.
6. What is the ligand over here?
So ligands are H2O, sir.
What is the central metal ion?
So nickel, sir.
Nickel. Charge?
2 plus, sir.
Right.
Plus, sir.
Similarly, chromium H2O whole 6 3 plus. Can anybody say how many ligands are there? Coordination number? 6. Okay. So we have 6. And what is the ligand again?
H2O.
What is the primary valency?
Chromium 3 plus, sir.
Right. Okay. Suppose I give you PTNH3 whole 4. Okay. 2 plus. Give it a try. Coordination number? Coordination number?
Sir, 4, sir.
4. Ligand? Central metal ion?
Plus.
PT2. V or say MnCO whole 6 plus. Come on, give it a try.
So when তারপর হচ্ছে CO তারপর Mn plus.
Right. So you now have got idea. All right. Mostly. Please tell me again what is going to be here.
এখানে হবে 4 তারপর NH3 তারপর Z12 Zn plus তারপরটাতে হবে 4 NH3 Cu plus.
4 NH3, again NH3, and this is Cu2 plus. This is Zn2 plus. Okay. right? All right. So let's go for some neutral complexes, okay? And I'm giving you CO NH3 whole 6 Cl3. See, in most of the neutral complexes, there is nothing outside the third bracket. All right. There is no charge over here. See. Then we have MoCO6. All right. PTNH3Cl2. You keep saying, okay. Now we have NiCO4. Then we have FeCO5. All right. Okay. So again, if I were to ask you coordination number or secondary valency, I can use any of the names. Then I am saying ligands, and I have said over here oxidation number. Okay. Yeah. So what is the coordination number over here? See, you have 3 and another 3. Here is 3 and another 3, so it is total 6. Ligands are NH3
NH3.
and Cl minus. Okay. NH3 is neutral. Cl is -1. If this is X, then what is? So we will say, therefore, X equal to +3. So it is cobalt +3. Understood how to calculate oxidation state? Clear hai?
Yes, sir.
Okay. Next, if I am saying
এখানে 7, 6, তারপর CO, তারপর হচ্ছে
CO তে কি 0,
0 হবে না।
yeah. If this oxidation state is 0, then what will happen? We will say MO is in 0 oxidation state. Yeah, please go ahead for the next one.
এটা হবে 2,
Yeah, again 2 and another 2, na?
4, তো হবে 4, তারপর হবে NH3Cl মাইনাস আর +2 হবে সাবস্টিটিউশন +2।
Very good. Next one.
এটা হবে হচ্ছে 4, তারপর CO আর Cl 0 হবে।
Next one.
এটা হবে 5, CO আর Fe 0।
ठीक है? Let's go for some anionic complex. Now this will be interesting for you because first time you are seeing an ion that is containing a metal inside it, isn't it? Have a look. CO Fe6 3 minus. This is an ion, but it is having a metal inside it. Sorry. Again, Ni CN4 2 minus. Okay. CO, Cl4, 2 minus. CO, Br4, 2 minus. Pb, I4, 2 minus. Fe, Cn6, 3 minus. Fe, Cn6, 4 minus. Okay. Now again, if I ask you coordination number or secondary valency, ligands, oxidation state or primary valency. Okay. Please say coordination number.
So 6, sir.
It is 6. Ligand,
Sir, 8 minus.
oxidation state,
So 3 minus, sir. CO3 minus.
plus 3.
What's answer plus?
Please try next one.
Number 4.
Right. Next,
Number CN,
minus.
CN minus.
So nickel,
Beta have Na plus.
Ni plus
Na 2 plus.
2 plus, right. Next one.
Beta have 4.
Hmm.
তারপর Cl minus তারপর CO2 plus.
Next one.
তারপর এটা হবে 4 Br minus আর হচ্ছে Br minus আর CO2 plus.
Very good. Next one.
তারপর এটা হবে 6 Cn minus 3 plus. AB 3 plus.
PB iPhone, na?
হ্যাঁ স্যার। তারপর এটা হবে 4 তারপর হচ্ছে I minus তারপর PB 2 plus.
Next one.
তারপর এটা হবে হচ্ছে 6 তারপর Cn minus তারপর AB 3 plus.
Next one.
তারপর এটা হবে 6 Cn minus AB 4 plus.
Fe2 plus.
AB 2 plus.
Okay, you will later on know this is called ferricyanide because here the oxidation state on iron is 3 and here it is 2. That's why it is called ferrocyanide. Okay. Do you follow? Ferri means iron 3, ferro means iron 2. Okay. So now some definitions basically. What is coordination number? Obviously what? Number of ligands in, I should write donor atoms, okay. This will give you a better meaning. Attached, because later on we will come to know about tridentate, bidentate, tetradentate, hexadentate ligands, okay. A particular ligand having 2 or more donor sites, okay, not only one. So that's why I'm saying donor atoms. Number of donor atoms attached to the central atom. That's it. Now this coordination number will depend on the type of metal ion. Depends on the type of metal ion. That means the size of the metal ion will dictate what kind of coordination number it will have. Okay. Of the orbitals available for the metal ion to link up with the ligands. Okay, that will decide the kind of orbitals that are present or available for the metal ion to link up with the ligands. That will decide the coordination number. Okay. See, the first transition series mostly shows 4,6 coordination number. Or we can also say that coordination number usually increases down the group. Okay. Now, what are basically ligands? क्या होते हैं ये ligands? These are Lewis bases that are linked to a metal via a coordinate bond. Please understand, since the metals are linked to these atoms or ligands via a coordinate bond, that's why these are called as coordination compounds. Okay. So what we can say about the metal? The metal now we can say is behaving as a Lewis acid, isn't it? If somebody is giving its lone pair to someone, then obviously that particular species is accepting electrons. So that's why we can say the metal is always a Lewis acid and the donor atoms are always the Lewis base. Okay. Now thing about the complexes. What is the meaning of heteroleptic, heteroleptic and homoleptic complexes? Okay. See, only when one type of ligand is present inside in the secondary valency, okay, or I am trying to say in the coordination sphere. One minute. Okay, that was the alarm for the that I have with you. So only when one type of ligand is present in the secondary valency, that is in the coordination sphere, uh, it is called homoleptic complexes. Okay, understood? Say suppose I give you FeCO5, right? I've used this complex before. Or say I'm giving you NiNH3 whole 6 2 plus. So this is having only one type of ligand inside it. That is why we will call these as homoleptic complexes. Okay. Now when there are more than one type of ligand present in the complex, these are called heteroleptic complexes. Okay, suppose, see there is a chlorine and ammonia, so these complexes are called as heteroleptic. Here obviously you are seeing for the metal ion Fe there is 5 molecules of Cn and 1 molecule of NO. So there are two types of complexes, ligands out here. So these are called heteroleptic complexes. Okay, understood? ठीक है?
Yes, sir.
Okay, now there is an interesting experiment conducted by Warner. Okay, on which we have some questions being asked. So let me just have a little discussion over it. So say suppose there is a beaker and we have this containing some solution. All right. This suppose almost wine red solution is present there. That is basically we are having the cobalt solution out here. Okay. Now initially what happens over here? Okay, we are basically getting from here violet crystals. Okay, from here we are getting violet crystals initially at the very beginning. All right, and then after certain passage of time, from the same soup, from the same soup, get some green colored crystals. Okay, from here we are getting some green colored crystals. Okay, this type of process is called fractional crystallization. Okay, so these are now giving you green crystals. So the first batch, you get some crystals, say it is violet, you pour the solution in a different beaker, you wait for a certain time, you're getting green colored crystals, okay? And you're collecting them. As you're getting them, you're collecting them. Say again some time passes away, say time t2, alright, and you keep the solution, that is, you keep the solution standing, and again from the same soup, what is happening over here? We pass it in another beaker. You are now getting from here purple colored crystals. Purple colored crystals. Say you're getting purple crystal. So same solution, right? So if you keep the solution and you go away, it will be what, a mixture of violet, green, purple colored crystals. Okay, but you have seen it, okay, and you have paced yourself that way, and you have understood. Okay, if I keep the solution for this much of time, I will get this type of crystals. I will decant it, and then from the same soup, I will be getting another kind of crystal, and I will that is how I will be isolating the crystals. Okay, and this process is now called fractional crystallization. Okay, again from the same soup. Okay, suppose he now gets, all right, yellow crystals. Okay, so he's getting yellow crystals now. Something inside tells him that all these particular things are different. Okay, sure by this time that every crystal that is having a different color, okay, they must be separate things, separate compounds. And just like for me, using some metathetic reactions, he understands that this purple colored crystal is COCl3 dot 5NH3. The green one is something like this. The violet one is basically this. So these are the formulas of the compound before assigning them, uh, using that technique that he has given, like the third bracket. But how this third bracket concept came, okay, how this concept of secondary sphere and primary valency came, I'm explaining that. Wait. And this one he says COCl3 6NH3. Okay. Now what he does some conductance experiments which I'm not going to discuss over here. All right. Doing conductance experiments, you can, or conductance measurements, you can find out how many ions are there inside a particular compound. Okay, that can be done. But I'm going to give another test that is much more qualitative in sense and quantitative. Okay, qualitative in the idea and quantitative you can measure it basically. So what he did, he took this particular complex, okay, and he added, say, COCl3 dot 4NH3. He added some excess amount of AgNO3. He measured this weight, he added this thing, and suppose for There he got an idea that one equivalent of this salt was giving him precipitate of AgCl 1 equivalent. But if you see carefully, then here there is 3 Cl. He should have got 3 AgCl, right? But he's not getting. He's only getting only 1 equivalent of chloride. So that means only 1 chloride is free, other 2 are not. From that, he got an idea. That means outside the third bracket there is 1 chloride, okay, and the other 2 chlorines or chlorides, they are linked to the cobalt and they are not free. That means, what I'm trying to say, that the cobalt is directly linked via coordinate bond to 2 chlorines and one of them is lying outside the secondary valency. So if you say a chloride, we are getting only against 1 equivalent of this salt, we are getting 1 chloride test of only 1 chloride. That means that 1 chloride is free. That means that 1 chloride is outside. Technically, that chloride is outside the coordination sphere, or you will write it outside the third bracket. That is what he indicated. That means these 2 chlorines are not free, but this 1 chlorine is free. What is the meaning of it? If you put this salt in water, this is going to split into this complex ion where this chlorine are not free because they are held to the cobalt and only 1 chlorine is released. Because only 1 chlorine is released, we are getting the test of only 1 chlorine when this salt is dissolved in water. Okay, that is the meaning of it. Now suppose, so he did this test for this one and he arrived that this should be the formula, sorry, this should be the formula for this particular violet crystal. Okay, so things that he had written before like this, after this experiment, he got only the test of 1 chloride ion, so he came out to this conclusion. Okay, again when he did the test for sorry, for the purple salt, okay, for the purple salt, okay, that is COCl3, isn't it, 5 NH3, okay, that is the purple salt, okay. And he added excess amount of AgNO3. Now if I tell you that we are getting 2 moles of AgCl for 1 equivalent of this salt, what will be your conclusion? How many chlorine are lying outside the coordination sphere? Bolo. How many chlorine are lying outside the coordination sphere?
So 3.
If you are getting the test for 2 chlorine, how many, that means how many chlorine are lying outside the coordination sphere?
So 2
2. That means you will keep, so when you write the formula, you will keep 2 chlorine outside and the rest of the things should be inside. That means the formula is what? This. Do you agree? Okay. Now when he took the yellow salt, which is again COCl3. This one, and he added again AgNO3 excess. Again, for one equivalent of this salt, he is getting 3 AgCl. So what will you say? How many chlorine are lying outside the third bracket? 3. So the rest of the should be inside. Yes or no? Bolo.
Yes, sir.
So that is how he came to the conclusion about these formulas for these salts, that the yellow salt is having 3 chlorine outside, purple salt is having 2 chlorine outside, whereas the green or the violet crystal is having only 1 chlorine outside. Am I clear?
Yes, sir.
Okay. So now this experiment is very important, regarding which questions are given in your exams. Okay. Now out here we will do the classification of ligands, and then we will end this class with this topic today. Ligands are classified on the basis of how many donor atoms it has. Okay. They are classified on the basis of how many donor atoms it has and binds to metal ion. So here we will come across a term called denticity. What is denticity? Suppose you have an apple. Say, and somebody bites this apple only using one teeth. Okay, only one. Or he's holding this apple all with only one finger. So he will be called monodentate. That is, it is binding with only one tooth, right? And if it is binding with two such tooth, then we will say
By.
bidentate. Similarly, if it is binding with three, we will say it is
Tri.
tridentate. So whenever we are talking about binding capacity, that is called denticity. Okay, that is called denticity. Understood? ठीक है ना? All right. So ligands can be broadly classified under this heading. Okay, let's have a look. We have ligands and we are classifying it with one or more lone pairs, ठीक है, of electron then no vacant orbital, to receive the back donated electrons from metal. So these are called innocent ligands, okay? Such as H2O, NH3, F minus, etc. All right. What can be the other type? Hold on. Vacant orbital that can be used to receive back donated pi electrons from the low oxidation state metal. Such as what? PR3, Cn minus, CO, etc. They can have lone pairs or they cannot have lone pairs. Okay, so another one can be without lone pairs. Students will consider this one. Okay, listen. Hold on. Without a lone pair of electron, but with pi bonding electrons. Okay, so donation can also happen from pi bonding electrons, such as ethylene. We have studied one salt called Gises salt, right? I said it is the first organometallic compound. There we had ethylene. It can be benzene. We will see systems like or cyclopentadienyl, like ferrocene, okay? Cyclopentadienyl. तो ये हम लोग सब देखेंगे आयन रादर, ठीक है? ये ज्यादातर हम लोग ऑर्गेनोमेटेलिक जो सेक्शन करेंगे उसमें ये आ जाएगा आपका, और बाकी तो नॉर्मल है वो हम लोग पढ़ेंगे. Now let's start with the monodentate ligands. Okay, तो उसमें मोनोडेंटेट लाइगेंड्स के बारे में पढ़ रहे हैं पहले हम लोग, ठीक है? तो इसमें ये आपका लाइगेंड टाइप हुआ, ठीक है? इसमें हम लोग उसका नेम बोलेंगे और फिर बाद में इसका फॉर्मूला, ठीक है ना? तो पहले अगर हमने कहा अमोनिया, ठीक है ना बच्चे? तो इसमें अगर हमने कहा अमोनिया, तो इसमें क्या आ जाएगा? ये NH3 है, दो ऐसे इलेक्ट्रॉन्स इसमें, तो ऐसे लिखेंगे इसको हम लोग, ठीक है ना? अगर मैंने कहा पिरीडीन, तो कैसे लिखेंगे? देख लो आप लोग, ऐसे लिखेंगे इसको. अगर मैंने कहा पिरोल, कैसे लिखना है? ऐसा है, तो इससे डोनेशन होगा. अगर मैंने कहा वाटर, दो लोन पेयर है लेकिन एक ही डोनेट हो रहा है, ठीक है बच्चे? तो डोनेशन को समझाने के लिए एक एरो यूज करना जरूरी है यहाँ पे, ठीक है ना। तो वैसे वैसे अगर आप THF को देखो, ठीक है ना, ऐसा डोनेशन है, तो ये क्या आपका टेट्राहाइड्रोफ्यूरान है। तो यहाँ मैंने जो भी किया है वो सब न्यूट्रल लाइगेंड्स है, देखो जरा यहाँ पे, ठीक है ना। तो हम लोग अमीन्स को बोल सकते हैं। तो अमीन्स में क्या आ जाएगा आपका, RNH2 आ जाएगा, ठीक है ना, या फिर R2NH आ जाएगा, या फिर R3N आएगा, ऑल अमीन्स, ठीक है ना। कोई अल्कोहल को पकड़ लो तो यहाँ पे ROH हो जाएगा। कोई भी ईथर को पकड़ लो तो ये क्या होगा, ROR, दो है जिसमें कि एक यूज होगा। ट्राई अल्काइल फॉस्फीन ले लो, ट्राई अल्काइल फॉस्फीन पकड़ लो, क्या होगा वो, R3P, ऐसा कुछ। एग्जाम्पल पे क्या हो सकता है, ट्राईफिनाइल फॉस्फीन हो सकता है, माने PPH3, ऐसा डोनेशन हो सकता है, ठीक है। ऑल हैलाइड्स क्या है, X माइनस, क्या हो सकता है, Cl माइनस, F माइनस, Br माइनस, I माइनस, ठीक है। हाइड्रोक्साइड्स, अभी थोड़ा नेगेटिव चार्ज वाला मोनोरेंटेड कर रहा हूं, ठीक है ना। हाइड्रोक्साइड्स जैसे कि ऐसे, एल्कोक्साइड्स, क्या होंगे एल्कोक्साइड्स आपके, कोई भी OR माइनस को ले लो आप, ठीक है ना। इसमें आप कार्बोक्सिलेट्स, कार्बोक्सिलेट्स को भी ले सकते हैं, जैसे कि R, एक से ही बाइंड किया इसने, तो ये भी हो सकता है आपका ऐसे। तो ऐसे तो बहुत सारे हो सकते हैं, मैंने कुछ का आपको नाम बोला है और बोला है देखो ये सब आपके मोनोडेंटल लाइगेंड्स के अंडर पे आ जाएंगे, ठीक है ना। समझ में आया, बोलो।
हाँ सर।
ओके, नेक्स्ट में अगर हम बोलेंगे कि बाइडेंटेड लाइगेंड से, देखो डेंटेड लाइगेंड से मतलब दो होने चाहिए ना। अब इसमें हम कैटेगराइज कर रहा हूं इसको एनायोनिक, तो इसको मैं बोल रहा हूं डाई एनायोनिक। डाई एनायोनिक बोलेंगे तो मैं सिर्फ एग्जांपल दिए जा रहा हूं, जैसे देखो ये क्या होगा, इसको कहेंगे कैटेकोलेट, कैटेकॉल से कैटेकोलेट, ओके। ये क्या है, बेंजीन डाइथायोलेट, कैटेकॉल जैसा ही दिखता है, सल्फर हो जाएगा यहाँ पे, ठीक है। कैटेकॉल को हम लोग शॉर्ट फॉर्म में लिखते हैं CAT-2, इसको बोलते हैं BDT-2। फिर आपका आ जाएगा ऑक्सलेट, इसको लिखते हैं OX-2, और ये ऑक्सलिक एसिड का एनायन है या कॉन्जुगेट बेस है, तो यहां से ये दो एरो ऐसे करेंगे तो ये आपका डोनर साइट्स होगा या डोनर एटम होगा, ठीक है। इथेन डाइथायोलेट अगर करोगे, इथेन डाइथायोलेट, तो ये आपका हो जाएगा, ये दो साइट्स होंगे डोनेशन के लिए। मैलेनो नाइट्राइल डाइथायोलेट, इसको हम लोग बोलते हैं Mnt2-, और स्ट्रक्चर वाइज ये क्या होगा, ऐसा। ठीक है, अब ऐसा बाइडेंटेड लिगेंड्स के बारे में बात कर रहे हैं जिसमें क्या है, 2 डोनर मोनोनेगेटिव, मोनोनेगेटिव, समझिएगा इसको। 2 डोनर एटम्स है लेकिन मोनोनेगेटिव है, जैसे क्या यहाँ पे देख लीजिए, मैंने यहाँ पे दिया है एसिटाइल एसीटोनेट, शॉर्ट फॉर्म क्या है, एक एक माइनस। ये क्या है चीज, जरा देख लो, ऐसा ऐसा, तो ये आपके 2 डोनर साइड्स है यहाँ पे, समझे ना। डाइमिथाइल ग्लाई ऑक्सीमेट या DMGH, it is used to for the chemical test of nickel, और ये थोड़ा डिफरेंट टाइप का है, इसमें थोड़ा देख लेना। यहाँ पे क्या होता है, ऐसे 2 नाइट्रोजन पे से डोनेशन है आपका साइड पे, डाइमिथाइल ग्लाइऑक्सिम है ये, और एक तो OH न्यूट्रल होगा और एक OH का H हटके ये माइनस होगा। यहाँ पे आप देख ले हो क्या कि डोनर साइट में ही नेगेटिव चार्ज है। DMG एक ऐसा लाइगेंड है जिसमें डोनर साइट में नेगेटिव चार्ज नहीं है, पेरिफेरी में या अपेंडेज में अगर कोई और जगह में आपका चार्ज है यहाँ पे, ठीक है। Negative charge is not on the donor atom. This is one important thing that you have to remember. Next one is 2-amino benzene thiolate, and this is what we have, a benzene, there is the S minus and then that is the NH2, ये डोनर एटम है और ये डोनर एटम है, ऐसे करके, ठीक है। ऐसा ही यहाँ पे भी हो सकता है, ये भी हो सकता है, रुको जरा एक मिनट, okay, so that is how it can be. All right, now if you're talking about bidentate ligands but they are neutral, okay, completely neutral, तो ये वाला देखो, ये भी यूज करेंगे हम लोग, इथिलीन डायमीन, ओके, and it is abbreviated as EN. These abbreviations you have to know. Bipyridine, this is called as BPY. How is it? Basically, you have a pyridine connected from two positions. So this is sometimes also called 2,2- bipyridine, okay? Because this is one. So this point is 2, point is 2. So it is also called 2,2- bipyridine. All right. We can also have another one which is called phenanthroline, also known as fen. So these are the two donor sites. It is called phenanthroline, or abbreviated as fen. All right. You may also have sulfates acting as bidentate ligands. All right. Or you can also have carbonates acting as bidentate ligands, like that. Okay, so this is sulfonate, carbonate. All right. Something like this. This is also acting as a bidentate ligand. All right. So I think we have covered till bidentate ligands today. I will take up the tridentate, tetra, and the hexadentate ligand next day. Okay. And we can today end the class.